A3. So this is the last problem I'm going to work on. So this, propane gas is one of the nation's most versatile sources of energy and supplies about 4% of our total energy needs, right? So, anybody who's ever watched King of the Hill, knows that some people are huge propane and, propane accessory fans. But we can also use it for chemistry problems and stuff like that. So the first question is, what is the delta H formation for propane, right? And so if we just simply look at the end of the packet, under the carbon part, right, we can look carbon, carbon, carbon. There's going to be one that is C3H6, right, or H8, sorry, not H6. That's a different thing. So it's the C3H6, and that gives us then a delta H formation of a negative 104. For C3H8, negative 104, and this is going to be in kilojoules per mole is that unit. The next thing is, right, the standard enthalpy of formation is defining the change of enthalpy when one, blah, blah, blah. Basically write out, right, what the elements are that form it, and so that way we can get the balanced equation in that case. And so, right, we only have carbon and hydrogen, and so carbon in its standard state, right, is going to be, carbon solid, right, it's going to be graphite in this case, and that's going to be, and then we have hydrogen, which is H2 gas at room temperature in 1 atmosphere, and that's then going to combine together to form C3H8 gas in this case. And so now all we have to do is just balance all of that out, and so there's 3 carbons in propane, so we just simply put a 3 in front, right? We have H2, H8 on this side, so that means we have to multiply this by 4, right? And so that right there is our balanced equation in this instance, right? And so that's what the balanced equation, right, for the heat of formation of propane is. Now looking at the reaction, right, for part C, right, it says, is this reaction endothermic or exothermic? Why? Right, so it's exothermic because we can see that the delta H of formation is negative, right? So that means it's giving off heat, and the reason for that, right, is you're going to be ending up forming a lot more bonds than you originally were doing. Right, there's a lot more bonds in C3H8 compared to in graphite or H2, right? There's bonds, in graphite between the different carbon atoms, but there's no like unique different atom bonding system that you get in that case. Same thing with H2, right? Each hydrogen is just simply bound to one other hydrogen, whereas in the case of propane, right, you have carbons bound to each other, and then hydrogens bound to those carbons as well. And so for every hydrogen, right, there's going to be then double the amount of bonds compared to H2 and so forth. So pretty exciting stuff. And that's why, it's an exothermic reaction, because it's going to be forming more bonds, right, overall. Part D, how many moles of H2 are needed to produce 1,090 kilojoules worth of propane according to the balanced thermochemical equation, right? So if we look at this right here, right, when we're doing just simply for 1 mole of propane formation, right, you're going to be giving off, only 104 kilojoules. So if you want to do 1,090 kilojoules, right, you're going to then have to do some increased amount of moles, so to say, right? So the first thing we want to do is we want to figure out how many moles of propane we're going to be forming, right, when we give off, 1,090 kilojoules. And then we can use our balanced equation that we have, from part B to figure out then how many moles of H2 are actually required in that case. So the first thing that we want to do is, figure out, right, we have this equation, right, where we have the delta H of the reaction is going to be equal to the number of moles of propane times the delta H of formation of the propane. So if we rearrange that equation, right, we get N is equal to the delta H of the reaction divided by delta HF of propane. So we take that, and so N is then going to be equal to the delta H of the reaction is negative 1,090 kilojoules. Divide that by our propane that we have right here. So what we have then is negative 104 kilojoules per mole. And so what we get now, right, the kilojoules cancels, the mole goes up top. So we have 1090 divided by 104 gives us 10.5 moles, right? So we want to produce, right, to produce that much energy, you have to produce 10.5 moles of propane in that case. And so then the ratio, right, of propane to, propane formed is that you need to use then 4 moles of H2. And so then to figure out then how many moles of H2 we have, all we have to do is just simply multiply this by 4. And so what we get is 10.5 times 4 gives us 420 moles. No, that's not right. 10.5 times 4. I was like, what am I doing? 42 moles, right, of H2 in this case. Right, and so that's how you work your way through that part of the problem. You just basically figure out how many moles of propane you're going to be producing to, for that much energy, and then just using your balanced equation to figure out then what you do next for it. Part E, how much heat is produced during the formation of 30.1 grams of propane. Very similar problem. Now it's just flipped, right? So the first thing we want to do is we want to figure out how many moles 30.1 grams of propane is. And so the molecular weight of propane, right, is going to be equal to, let's see, so we have 12.01, which is the mass of carbon, times 3, plus 1.01 times 8, which is the mass of the hydrogens. And so that comes out to 44.11 grams per mole. Right, that's the molecular weight. And so then now the number of moles that we have is just simply 30.1 grams divided by 44.11 grams per mole. So the grams cancels, moles goes up. 30.1 divided by 44.11 is 0.682 moles. Right, and so that's how many moles of propane we want to form. And so now we want to figure out how much energy is going to be released in that case. And so the delta H of this reaction is going to be equal to the number of moles times the delta H of formation of the propane. And so we plug in our numbers, right? So we have 0.682 moles. And that's going to be multiplied by, negative 104 kilojoules per mole. So the moles cancels. We only stick with kilojoules. What we get is 0.682 times negative 104. We get negative 70.93 kilojoules. Yeah, it's the same thing, right? And so in this case right here, right, and so I guess the amount of heat that it's giving off from the reaction is 70.93. The way that I wrote it out in terms of the key, right, I said I had it as positive 71. Right, I'm just simply saying, right, that's how much is produced, right? So it's going to be 71 kilojoules. So it's the same number, right? It's just simply differences in terms of how I'm framing it, because the amount of heat that's going to be released to the surroundings, right, is going to be 71 kilojoules, right? So that's going to be Q in that case, right? So you have to, I guess, think about how specifically a problem is worded, whether or not it should be positive or negative, right? Again, this comes back to thinking about what your system is, what your surroundings are, and so forth. But the delta H of the reaction is this right here, right? So that's how much heat's going to be produced and given off. And so if I'm asking, right, how much is produced, right, that's going to be then, should be a positive number in that case, right? Because I'm already asking how much is produced in that case, which is why you would want it to be a positive number like I have on the key. F, write a balanced chemical equation for the complete combustion of propane. What additional reactant is necessary for a combustion reaction? Hopefully this is something you guys learned in Chem 100 or in AP chemistry, right? But combustion reactions, require oxygen for it. And so in this case right here, right, you have to add oxygen as a reactant, and what you should be producing, if it's a clean reaction, is carbon dioxide and water as your products in this case. And so if we go through, right, and write out, right, so we have C3H8 gas plus O2 gas yields CO2 gas plus, and this is kind of where things differ between people. Some people proclaim, right, that it forms liquid water. I like to say produces, gaseous water, like, because usually you always have steam and then it condenses. But either is fine, right? So I just simply wrote it out as gas in this case. And so you get H2O gas in this case right here. And so now if we balance this out, right, so we're going to have 3 moles of carbon. In that case, we're going to have 4 moles of H2. And so that means overall we have 6 plus 4, right? There's 10 moles of oxygen. So that means we have to have a 5 in front of the oxygen right there. Right, so that's all balanced out. So then the next thing is, right, calculate the delta H of the reaction for the combustion of propane using the delta HF table and Hess's law, right? So in this case right here, this is going to be a scenario then where we can just simply calculate the delta H of this reaction by doing the sum of the delta HF of the products minus the sum of the delta HF of the reactants. So we take that, right? Our products, we have CO2. So this is going to then be 3 times. So if I look at the back of the table, right, for carbon dioxide, so CO2 gas, we have negative 393.5 kilojoules per mole, plus for the water, we have 4 times, so H2O gas, so that is negative 242 kilojoules per mole, right? So that's all of our products. Now we subtract out our reactants, so minus, and so we have C3H8, so that's going to be 1 mole of C3H8 times negative 104 kilojoules per mole, plus oxygen, right, is one of the elemental forms, and so it has a 0 value for the delta HF in this case, right? So it's going to be 0 in that instance. So if we take all of that and add all of it up, what we get is 3 times negative 393.5 plus 4 times negative 242. So we get on the product side, we get negative 2,148.5 kilojoules in that case, minus negative 104 kilojoules, right? So this is 1 mole, right? Because the moles then cancel. Right, so we have all of that. So now if I just simply subtract negative 104 from that value, what we get is negative 2,045 kilojoules, right? I'm just going to round it up a bit. Right, which should be what I have on the key. Negative 2,045 kilojoules, right? So that's how you do that right there, right? So again, this is just the Hess's law problem. You just look at products and reactants and how all of those interact with each other. So, and that's it. That's everything that everybody